If we don't carefully choose which numerical method we are using to simulate the solutions of certain dynamical systems, such as something as simple as the harmonic oscillator, what can happen is that we reproduce a behavior which is completely unphysical and unnatural. For example, in this case, you can see at the top a simulation of the simple harmonic oscillator with a method which is the simplest one, and it is actually the explicit Euler method. And you can see that the simulation is extremely unstable, so the energy blows up, and we don't get something that we expect, right? So we would expect a behavior which is pretty stable and boring if you want, and the behavior we're looking for is exactly the one that we are recovering at the bottom. So at the bottom we are using a different numerical method, which I'm going to discuss a bit further in the next few slides. And this second method is designed so that it conserves the quadratic energy function that is supposed to be conserved by the exact solutions and hence also by the numerical solutions of this system. So let's try to inspect a bit more the situation we are studying here and let's understand what's going on. So the system that I was simulating in the previous slide, in the introduction, is probably the simplest non-trivial equation one can study, which is the one of the simple harmonic oscillator. It's a linear oscillator. It can be seen as an approximation, the linearization of the simple pendulum, for example. And we have a second two-dimensional system with linear equations. So q prime is equal to p, and p prime is minus q. So you can think of p either as the conjugate momentum or as the velocity if the mass is equal 1. So we have a particle, which is our mass here, point mass here, that is attached to a spring, and we can describe the dynamics through this simple set of equations. The interesting aspect that we're going to discuss in this video today is that this system, despite being very simple, it has an important property, which is that the solutions of these equations conserve a quadratic energy function, which is, from the point of view of classical mechanics, just the mechanical energy, the kinetic plus potential energy of the system. So this is also called the Hamiltonian of the system, and it's a function h of qp, and is simply given by the Euclidean norm squared of the vector qp, so q squared plus p squared, and we divide by 2 just for convenience. And the simple way to see that this is actually a conserved quantity, a first integral of the dynamics, is by differentiating the Hamiltonian energy or the mechanical energy along solutions. So we consider q and p as functions of time because they are assumed to be solutions of this system of equations. And we differentiate with respect to time this composite function. So what we get here is nothing else than q times q prime by the chain rule, and the prime here stands for the time derivative, plus p times p prime. Now q prime and p prime are well defined, and we know what is their value, what's the expression behind them, simply because they are described by the equations that q and p solve. So q prime is nothing else than p, and p prime is minus q. So we replace this here, and we see that this is leading to a 0 value. So this means that this quantity here on the left is 0, which means that h evaluated along solutions is a constant value, takes a constant value. So more explicitly, what we are just discovering is that what we have at time t, which is q squared at time t plus p squared at time t over 2, so the energy at time t, is equal to the energy at time 0. So the energy at time 0 is fully prescribed by the initial conditions. So it's nothing else than q0 squared plus p0 squared over 2. So geometrically, we can also think of what is going on here because it's fairly simple. And this means that the solutions described by the pairs qt and pt are evolving along circles, and the radius of the circle is defined by the initial condition. So essentially we are saying that we shouldn't get farther or closer to the origin than we are at time 0. So in practice, this is exactly also what we are trying to reproduce numerically when we discretize the solutions with a numerical method such as Runge-Kutta schemes. Now, going back to the animation I showed at the beginning, let's try to plot this kind of situation in a slightly different manner to get a feeling of what is going on in in an easier way. What I'm going to show you now is a pair of simulations obtained with two different methods, both which are second order accurate. So they are supposedly equally good at simulating the equations from a quantitative standpoint. But we can see that this method, which is an explicit second order method, is Euler-Heun, is just a modified version of explicit Euler method. What it leads to is a blow up in the energy. So we start at time 0 from position 1, 0 here in the red dot. And what happens is that the solutions are out spiraling. So we will get farther and farther from the origin as time progresses. So you can see that the energy is varying in a quite clear manner. So if we plot the logarithm in base 10, it doesn't really matter, of the difference between the energy at time t and the energy at time 0 in absolute value, you see that there is a blow up. So this is actually what we want to avoid, because it means that we are not conserving the expected conservation law of the exact solution. On the other hand, if we use the implicit midpoint method, which is also a second order method, but this is in terms of quantitative accuracy, but you can see also qualitatively that the performance is completely different. So we start here and we end up here. And what happens is that the distance that this point has from the origin is exactly the same as the distance it had in position in the red point here, so at the initial condition. And in fact, you see that the energy variation is negligible, especially in machine accuracy. In fact, you have something of the order of 10 minus 15. So now what I want to do in the final part of the video is try to explain why this is happening. And in fact, the question is not trivial to answer to, because in principle, the two methods are supposed to be equally good in terms of quantitatively approximating the solution. And in fact, they are. In fact, they are both second order methods, which means that this Cian position here and this Cian position here are in principle equally far away or comparably far away from the exact solution. The difference is that the two methods compensate differently or accumulate errors in a different way from the geometric standpoint. In fact, this method here, while accumulating errors for sure, it still guarantees that the position remains on the correct level set of the invariant energy, in particular on this circle defined by the initial condition. On the other hand, what happens here is that this guarantee is lost, because this method is not structure preserving. Why is their long-time energy behavior quite different? Well, the answer is that we don't have to look for an answer in terms of accuracy or differences in accuracy of these methods, but in the structure that these methods have. These two methods are both Runge-Kutta methods, and the very appealing aspect of these methods is that most of their properties and their actual expression are fully characterized by what we can say is their DNA, which is the Butcher's tableau. So this is nothing else than a collection, a triple of three objects, which are either matrices or vectors, that fully describe the update behind those methods. So each of the Runge-Kutta methods is defined by a number of stages, of steps that we need to perform to define one update of the solution from time t0 to t0 plus h, for example. And we have a matrix, which is the tableau matrix A. It's a square matrix of size s times s. And for explicit methods, is a strictly lower triangular, so it has zeros on the diagonal. C is a vector of s entries, and B is a row vector of s entries. So if we want to look for an answer of why the implicit midpoint method is better in some sense than the Euler-Heun method, we should look for answers in the structure of this matrix A and how it combines or relates with the vector C and B. The secret to conservation, so to conserve quadratic invariants, quadratic first integrals, is that there must be a very specific relationship between the coefficients of the tableau, and in particular between the matrix A and the vector B. So this condition can be characterized in two equivalent ways. One in terms of S squared scalar conditions and the other in terms of a matrix condition. A method, up to some technical assumption which is not too important here, is conserving all quadratic invariants, and the all is important here, if and only if there is this condition on the tableaus. And there's a simple exercise that I suggest you to think a little bit about. You can easily show that this condition is never satisfied by explicit methods. And I remind you that a method is explicit if and only if it is defined by a matrix A, which is strictly loaded triangular. In fact, the implicit midpoint method is a method of one stage, so S is equal 1, A is 1/2, B is 1, and C is 1/2. And what we can easily see is that M, in this case, and in this case, since S is equal 1, the two conditions are actually one and the same, is defined by Bi, so B1 times A11 plus B1 times A11, so it's 2 times the same entry. And that entry is just 1/2 times 1, so it's just 1, minus BB transpose, or B1 times B1, is exactly 1. So you see easily that this condition M equals 0 is satisfied by this method. So if we trust this result, we can also see why that method is much better in terms of conserving the desired qualitative structure of the underlying dynamics. I want to conclude with a preview of what will be a bit of the program, the schedule for the next few videos, because I think these ideas are interesting per se, but these ideas are actually very important for many more reasons. In fact, one can fairly easily see that the methods we have been studying, so the condition we have been seeing about the tableau, is exactly the same behind symplectic Runge-Kutta methods. So one can use this kind of methods, this kind of property, to design methods conserving some other geometric invariant of Hamiltonian systems, and that's great for long-time simulations. And also, very similarly, one can design a condition very, very close to the one we saw to get what are called bistable methods, or that are methods that conserve the contractivity or non-expansiveness of the exact solution. And we can discuss this in later videos. And so there's a lot to talk about in this area, and this was more like an introduction to what is more like a very broad field, the one of geometric numerical methods. This is everything for this video. If you have questions or ideas for future videos, let me know in the comments. Otherwise, see you in the next one. Bye.